Okay. Now let's get on to curve sketching. So, a question that you'll sometimes be asked in a calculator free exam is to sketch a curve, and most people do not like this topic, myself included, so don't feel too bad if you're kind of dreading this right now. It does get better when you understand and you've practiced a lot, because then it gets a lot easier and you don't really hate it as much, but the key really is to practice it and know a lot of the methods, all right? When you're sketching polynomial curves, it's quite easy because a lot of the derivatives are easy and you kind of already know, like, based on what polynomial it is, what it looks like. But a lot of the time you'll get like kind of a complicated curve, and it will include a few different types of functions, and you'll kind of look at it and have no idea what it would look like at all, like not even a vague picture, all right? Like now if you get, a function and it has a cubic in it, you know vaguely what it's going to look like, so that it helps. But sometimes you'll get one where nobody can look at it and know what it looks like, not even your teacher. So it's just kind of, it's more like feeling in the dark, which is a lot more difficult, but it also means that any question like that will be worth a lot more marks. So there's that. Anyway, let's get on to stationary points. So if you have been asked to sketch a curve and you need to find the stationary points on the curve, which you always will need to do, you'll need to find where there's any stationary points on the curve so you can sketch those. There's two methods for determining what the nature of that stationary point is. And by nature, I mean whether it's a maximum, a local maximum, or a local minimum. All right, so a maximum looks like this, a minimum looks like this. Okay, so because sometimes you'll figure it out, you go like, oh, there's a stationary point here, but does it go like this, or does it go like this? All right, and you've got to figure it out. So there's two ways to do this. The first way is the first derivative method, which is to create a table of values with the first derivative. All right, and from here, you can determine what type of stationary point is. So say we had our stationary point at 2, so obviously our first derivative then would be equal to 0. So remember, the stationary point occurs when the derivative equals 0. Say you did your calculation and you figure that on this side the first derivative is negative, on this side it's positive. What I always tend to do, which makes it easy, is to just kind of like draw lines underneath this. So if we have a negative gradient, it's going to look like that. A gradient of 0 to be flat. Positive gradient will look like this. So we know that that's a minimum. Right, and vice versa. It's positive, 0, negative. We know it's going to be positive here, 0, negative. So that will be a maximum. All right. Then if you get the same value on both sides, like positive, straight, positive, you know that that's a horizontal point of inflection. Sorry, horizontal stationary point. The other way that you can do it is to substitute your x value into the second derivative. All right. So you can get the x value and put it into the second derivative, and the value that you get from that will tell you whether you have a maximum or a minimum. So if your second derivative is positive, then you have a local minimum. If your second derivative is negative, then you have a local maximum. Alrighty, let's go over an example here. So first we need to find the first and second derivatives. Alright. Now we need to find any stationary points and determine their nature. So remember, a stationary point occurs when the first derivative is equal to 0, so we're going to have 0, equals 3x squared minus 3. 3 equals 3x squared. Right? 1 equals x squared, meaning that x equals plus or minus 1. Now we need to determine the nature of these. So what I'm going to do here, because our second derivative is so simple, we're going to use our second derivative. We're going to have double dash negative 1, double dash 1. So the second derivative will be negative 1 will be negative 6, and positive 1 it'll be 6. So remember, when our second derivative is negative, it means we have a local maximum. When our second derivative is positive, it means we have a local minimum. So that's how we can classify those stationary points there. Now let's get on to determining any inflection points. So remember, an inflection point occurs when the second derivative is equal to 0, and that's our first requirement. So we're going to go 0 equals our second derivative, which is 6x, giving us that x equals 0. Remember, our second requirement for a point of inflection is that the concavity around that point changes. So let's do a table of values. We're going to have x, and then our second derivative. So 0, and then just pick two numbers on either side. So I'll pick negative 1 and 1. It's always best to kind of like pick nice, easy numbers. So our second derivative is 0. And actually, oh no, that doesn't matter, sorry. At negative 1, our second derivative will be negative. At 1, our second derivative will be positive. So this tells us that there is a point of inflection at x equals 0, because both of those requirements were met. Alright, let's move on. Let's continue on with this question here. So here we need to find the first derivative and show that it is equal to that factorized form there. Then find any stationary points and use a table of values to determine their nature. So pause the recording, have a go at this yourself first, and then we will go through the solution. So as you might be able to tell here, to derive y might be a little bit difficult, depending on how much of the year 11 content you remember. So, remember, to derive a function to a power, you need to use the chain rule. To derive a function to a power, you need to use the chain rule. Alright? So here, we have a function to a power. What else do we have? We have a product. When you have a product of two functions, you need to use the product rule, right? So when you have a product between two functions, you need to use the product rule. When you have a function to a power, you need to use the chain rule to derive. What do I mean by a product between two functions? By function, I don't just mean like kind of any old number. I mean it has to be a product between two x's. So in here, we have a multiply, and on either side, we have an x somewhere. If you just have 5x, you don't need to use the product rule here, because 5 isn't a function, it's just 5. Alright, there's no x. But if you have like x multiplied by like sine x or something like that, obviously on both sides you have an x. So, let's start by deriving. If you ever get confused about which derivative rule you need to use, which one you need to use first, I should say. Like, do we need to use the product rule first here, or the chain rule first here? Always what you need to do is look at like the most basic structure of the function. So here, I can tell that we do have a function to a power. But the most basic structure is the product. Alright? That's the most basic thing you need to do. So we're going to let u equal x and v equal x minus 2 cubed, u dash equals 1, and here we need to derive that function there. So now we need to use the chain rule, right? So we're going to take the old power there, leave those in the brackets, leave what's in the brackets as is, take 1 from the old power, and then multiply by the derivative of what you covered over, which was this part here. So the derivative there is only 1, giving us 3 times x minus 2 squared. So now to continue on with our chain rule, with our product rule, we're going to have u times v dash plus u dash v. So we're going to have 3x x minus 2 squared plus x minus 2 cubed. Alright. So now we obviously need to get this into the form that it is in there. So the first thing that I notice is that x minus 2 squared is factorized out. So let's factorize out x minus 2 squared. We're going to have x minus 2 squared inside of 3x plus x minus 2. Alright, and now let's see what we can do in these square brackets. So we're going to have 3x plus x, which is going to give us 4x minus 2. Alright, and now as you might be able to see, the only difference between what we've got so far and what we need to prove is that 2 is factorized out. So we can say that this is equal to, instead of 4x take 2, we can take the 2 out to leave us with 2 times 2x minus 1, and then x take 2 squared. Alright, and this is our answer. Now we need to find any stationary points and use the table of values to determine their nature. So to find a stationary point, we need to let the derivative equal 0. So we're going to have 2x outside of x minus 2 squared. Alright, so let's go through and solve this here. We can use the null factor theorem. So we can let 2x minus 1 equal 0 and x minus 2 squared equal 0. So we're going to have x equals a half or x equals 2. Alright. Now what we can do from here is we can determine their nature, and I actually might just do this using a table of values. So we can have x here, our derivative here, a half, 2. So we can have 0, 1, and 3 in between. Alright, so we know that at those points our derivative is 0. At 0, what is the value of our derivative going to be? We're going to have 2 times 0, so times negative 1, times negative 2 squared. So this is going to be negative here. Dash of 1. We're going to have 2 times 1 times 1, so it'll be positive here, and then f dash at 3, we're going to have 2 times 5 times a positive number, 1, so that'll be positive there, I believe, times 1, positive, yep, and then 3, we're going to have positive there, yep. So that means our curve will look something like this, negative, positive, positive, it will flatten out and then be positive again, alright? So this one will be a minimum, and this will be a horizontal point of an stationary point. Right. Now let's go through this question here. So we have a curve y equals ax squared plus bx plus c passing through the point 1, 4 and negative 1, 6 and obtaining a maximum value when x equals negative a half. Find a, b, and c. So we've been given a coordinate on the curve, sorry, 2 coordinates on the curve, and a value about its stationary point, its maximum value. So what we need to do here is we need to use these 2 points to find any unknowns in the curve, and then we'll use that to incorporate the derivative there. So we are going to sub in our 2 values. We're going to have 4 equals a times 1 squared plus b times 1 plus c. So we're just subbing in that first coordinate there into our curve. Now we're going to sub in our second coordinate into our curve. So we're going to have 6 equals a times negative 1 squared, which is just a, minus b plus c. Alright. Now we know that it obtains its maximum value when x equals negative 0.5. So let's find our derivative. So we're going to have 2ax plus b. We know that the maximum value will be occurred when the derivative is equal to 0. So we're going to have 0 equals 2ax plus b. And we know that x equals negative 0.5. So we can also sub that in, right? Which will cancel out that too. So we're going to have negative a plus b equals 0. Or in other words, a equals b. We can use this to substitute back into these 2 equations here. So we can have, given that a equals b, we can have 4 equals 2b plus c. 6 equals a minus b. Alright, just give us c. Because a minus b, the same number, taking the same number. We can pop this back in here. So we will have 4 equals 2b plus 6. Alright, 4 minus 6 is negative 2. So b equals negative 1, giving us that a is also equal to negative 1.